Pluto is far away from the Sun, of course, so the Sun is multiple times fainter than it is here on Earth. Consequently, the planet experiences freezing temperatures, decreasing to around -230 degrees Celsius during the evening. In an intensity wave, it could get as high as 170 degrees Celsius. Pluto has an exceptionally shaky climate too. Welcome inquisitive minds to an investigation past the recognizable domains of our solar system. Consider the possibility that I tell you Pluto, the far-off and confounding dwarf planet, is finally taking its cosmic action, potentially crashing into none other than Neptune, the ice giant. Pluto's defiant nature has been obvious from the start, a rebel on the edges of our heavenly area. Its orbit boldly running into another planet challenges the traditional standards of planetary conduct. I mean, that's no sort of behavior for a planet, right? From the baffling complexities of Pluto's orbit to the raised concerns voiced by astrophysical luminaries like Tyson and Kaku, a lingering question hangs in the cosmic balance. Will these celestial giants be on a collision course? Could the convergence of their paths spell unanticipated ramifications for our beloved planet Earth? Today we embark on a cosmic journey filled with uncertainty. While the answers to these celestial inquiries might evade us right now, the potential for a collision of such cosmic magnitude serves as a stark reminder that the universe is a stage for events both dazzling and perhaps alarming. Join us as we delve into the mysteries that orbit our understanding of Pluto and Neptune, considering the possibilities of a celestial conflict that could reshape the cosmic equilibrium of our solar system. The stage is set, and the unfolding drama beckons us to witness the enigmatic dance of the planets among other potential space catastrophes. The universe harbors a variety of riddles, and among them is the intricate puzzle known as the three-body problem. Yet, researchers predict other likely disasters within the celestial theater. Although a planet crashing into another in space is highly improbable, it is not entirely out of the question. Gravitational interactions, as depicted by the three-body problem, are one of the forces that influence planetary orbits. An example of a space system where gravitational forces produce a periodic pattern known as orbital resonances is TRAPPIST-1, which has 7 Earth-sized planets. As time passes, these patterns could destabilize planetary orbits, increasing the likelihood of collisions. In the case of TRAPPIST-1, no collisions have occurred, despite the system's density and the mutual influence of the planets on each other's courses, especially when they are close. Scientists routinely monitor these systems to understand how planets move through space. Another little-known phenomenon is rogue planets, which drift randomly in space rather than orbiting a star. Removal of planets from star systems can occur due to gravitational pulls or other cosmic phenomena, such as a nearby star's approach or dynamic instability in multi-planet systems. Over time, these wandering planets can travel great distances, perhaps even reaching areas far from where they originated. It is conceivable that they will run into other star systems on their solitary journeys. The probability of a planet collision increases if one of these planets ventures into another planetary system. Regardless, a rogue planet striking another planet head-on is highly unlikely, considering how vast and mostly empty space is. The sparsity of planets in open space and the enormity of interstellar distances work together to prevent frequent collisions. It is already highly improbable that 2 rogue planets will collide, yet the frequency of rogue planets is far lower than that of stars and planets in stable orbits. However, star systems can become chaotic during a cosmic merger. It is highly unlikely that planets will collide head-on during these enormous events due to the vast interstellar distances. The orbits of stars and planets in merging galaxies are drastically altered by the intense gravitational forces. A planet might become a rogue world, liberated from any star, when this kind of chaos drives it out into the cold, dark depths of intergalactic space. On the other hand, planets could be ejected from their orbits, collide with each other, or even affect their host stars due to these gravitational disturbances. When gas and dust are compressed under extremely high pressure, gravitational enhancement can actually cause new celestial bodies to form or perhaps ignite stars to emerge. In our solar system, the late heavy bombardment suggests that around 4 billion years ago, there was a period of increased collisions involving comets and asteroids. This surge in impacts is believed to have resulted from gravitational disturbances caused by the outer planets during this chaotic phase. Gas giants like Jupiter and Saturn were undergoing migration, disrupting the orbits of numerous smaller bodies in the Kuiper Belt and asteroid belt. As a result, these smaller objects were thrown into erratic paths, with many advancing into the inner solar system. This influx led to a significant rise in impacts on the terrestrial planets, including Earth. While these impacts did not involve direct collisions between planets, they show how gravitational interactions can bring about major shifts in the courses of celestial bodies. This bombardment is thought to have played a crucial role in shaping the surfaces and geological histories of planets in our solar system. Additionally, it might have contributed to the delivery of water and organic materials to Earth, influencing the development of our planet over an extended period. As stars undergo changes in mass, the orbits of planets around them might shift and potentially cross. This is especially noticeable in systems where stars are at the end of their life cycle. As a star ages and consumes its nuclear fuel, it often undergoes significant mass changes, particularly during stages like the red giant phase or when it releases material in a planetary nebula. These variations in stellar mass can significantly affect the gravitational balance of the system, causing the orbits of nearby planets to either move outward or become more compact. This is more likely to occur in multi-star systems where complex gravitational interactions can easily lead to unstable orbits. In such systems, the gravitational forces from multiple stars can interact unpredictably, exacerbating orbital shifts and increasing the chances of orbits intersecting. This can result in situations where planets could get captured by another star, collide with other celestial bodies, or even be ejected into interstellar space. Pluto's unusual orbit, initially recognized as a full-fledged member of the Planetary family, underwent a reclassification, eventually being designated as a dwarf planet due to its distinctive orbit. The astronomy community is still enchanted by it and finds it fascinating. Despite this change, there's reason to worry about the proximity of Pluto's path to Neptune's. According to recent estimates by notable scientists like Neil deGrasse Tyson and Michio Kaku, these researchers are sounding the alarm about a grave danger to Earth, the possibility of a collision between the planets. Pluto is unlike any other planet in our solar system, and this is what makes its orbit around the Sun so remarkable. Pluto has not completed a full revolution since its discovery in 1930, and its orbit spans an extended 248 years. The fact that it deviates significantly from the generally circular orbits of the major planets makes its path highly eccentric. Adding to Pluto's orbital complexity is the combination of its elliptical shape and inclination. The point where Pluto's orbit intersects with Neptune's is an intriguing feature. During roughly 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, challenging expectations based on their respective positions in the solar system. This prompts the question, why hasn't a collision between Pluto and Neptune happened? The explanation lies in the gravitational effects exerted by other planets. The assessment of Pluto's orbit began shortly after its discovery, presenting a complex trajectory for astronomers. Unlike most planets, whose orbits align relatively close to the ecliptic plane, Pluto's unique characteristics include a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune. The three-body problem, which describes the gravitational interactions of three celestial bodies, helps to explain Pluto's orbit stability amid its complexities. Understanding the movement and gravitational interactions of three celestial bodies like Pluto, Neptune, and the Sun is known as the three-body problem in space. Predicting their trajectories from their initial positions and the effects of gravity on each other is crucial. For Pluto, some terms that help address this astronomical mystery are azimuthal libration, latitudinal libration, and the VZK oscillation. According to astrophysicists, azimuthal libration is significant because it keeps planets in their orbits. When Pluto crosses Neptune's orbit, it is at least 90 degrees away, which is a critical distance that prevents collisions. Latitudinal libration, referring to the vertical movement of a celestial body in its orbit, ensures that when Pluto approaches Neptune or other giant planets, it is positioned significantly above their orbital plane, providing an additional layer of protection against collisions. A key factor in understanding this is the gravitational interactions between three space objects, such as Pluto, Neptune, and the Sun. The VZK oscillation explains why Pluto's orbit around the Sun seems irregular but remains smooth over time. Despite the apparent randomness in space, fundamental patterns and rules maintain order. Collectively, these factors stabilize Pluto's orbit, preventing collisions with Neptune or deviations from its path. The three-body problem helps us understand how the gravitational pulls of these space objects influence their trajectories. This knowledge adds to our understanding of Pluto, our solar system, and distant celestial bodies. Mathematical simulations in the late 1980s revealed that despite its stable properties, Pluto's orbit is indeed chaotic, with minor initial deviations leading to significant differences over thousands of years. Orbit stability notwithstanding, Pluto's unique orbit exhibits remarkable stability over extensive periods, effectively mitigating potential chaos. Recent simulations have expanded our perception of the complex dynamics involving giant planets like Neptune, Jupiter, and Saturn affecting Pluto's path around the Sun. Neptune's specific gravitational influence, completing 3 orbits for every 2 of Pluto's, substantially contributes to the overall stability of Pluto's orbital path. Jupiter's gravity is also significant but less so than Saturn's. Taken as a whole, these observations paint a picture of Pluto